Okay, welcome back everyone. I'll just pin myself briefly. Welcome back to the second part of the final session on methods and method development. We've got 3 speakers this afternoon, and I won't spend any more time introducing it. Let's just get started. We're going to start with Matthew, and the floor is yours. Go ahead.
Thank you, David. Right. Good afternoon, everyone, and thanks for attending this talk on my PhD project, which has been about developing an effective Hamiltonian for a proton transfer ferroelectric material. So just to give a brief background for my project, which is the study of ferroelectricity, which is the presence of a switchable spontaneous electric polarization in a material. So ferroelectric materials typically have ferroelectric phases and paraelectric phases separated by a phase transition at a temperature known as the Curie point. If an electric field beyond a threshold known as the coercive field is applied to a ferroelectric material in its ferroelectric phase, then the direction of the polarization can be switched. And this phenomenon is exploited in numerous applications, for example, non-volatile memory chips. Non-volatile in this context, meaning that the state of the memory isn't lost if the power is switched off. The remnant polarization is the polarization which remains after the external field is removed. So most applications of ferroelectrics involve inorganic ferroelectrics, and so most experimental and theoretical research into ferroelectric materials and the polarization switching dynamics have focused on this class of materials. So I decided to study organic ferroelectrics since less is understood about their domain dynamics. The example that I focused on during my project has been croconic acid, which is a room temperature proton transfer ferroelectric, which basically means that the ferroelectric switching is achieved by the transfer of protons in between, across a gap, the gap between the surrounding oxygens, which are kind of illustrated in the 2 figures at the bottom of the slide. Structurally, croconic acid consists of folded sheets of C5O5Hd molecules, and it has remnant polarization and coercive field values which are similar to commercially exploited inorganic ferroelectrics. However, it thermally decomposes at around 450 Kelvin before it ever reaches a paraelectric phase transition. So although less is known about domain wall dynamics in organic ferroelectrics, there has been some research into imaging of domains in croconic acid in particular. In 2014, investigators, they imaged the nucleation and growth of domains in croconic acid by illuminating a plate of croconic acid with 100 femtosecond laser pulses and measured the terahertz radiation that was transmitted by the material. In particular, the phase and the magnitude of the transmitted radiation could be used to deduce the local direction and magnitude of the polarization on the plate. So with this technique, they were able to visualize the motion of 180-degree domain walls in croconic acid. However, the spatial resolution of this technique is limited to 16 microns, which is the width of the laser pulse. And so I've been interested in using theory and simulation in order to predict the structure and dynamics of domain walls in croconic acid. So traditionally, ferroelectricity is understood in terms of the softening of modes at the gamma point of ferroelectric material. However, in our previous work, we found that at least 8 phonon modes are needed to accurately produce the potential energy curve along the minimum energy path between chloronic acid's domain states, as predicted by the nudge elastic band algorithm, which shows that a limited number of phonon modes isn't sufficient to accurately capture ferroelectricity in this material. So, to make progress in understanding the domain dynamics in chloronic acids, we decided to use the approach of constructing an effective Hamiltonian for the material, which is essentially a computationally efficient approximation to the potential energy surface. Virgil and Escorihuela Sayalero constructed they defined an approach to constructing an effective Hamiltonian for strontium titanate, which is essentially a Taylor expansion of the energy in atomic displacements and strain. And they used their model to study computing lattice instabilities in the material. So this approach involves generating a training set of first principles data, so atomic displacements, forces, strains, and stresses relative to the high symmetry phase. So in the case of strontium titanate, the high symmetry phase is the PM 3 bar M space group. What's also necessary is to generate a pool of possible terms in the Taylor expansion, which are consistent with a certain spatial cutoff and limit to the number of coupled bodies in the term, and then to group terms which are space group symmetry related, which would therefore have the same expansion coefficient, and then the mean squared error of the forces and stress is minimized with respect to the expansion parameters. A forward selection algorithm is used in order to select terms from the pool to add to the model, and this algorithm and the generation of the pool of terms is implemented within the Abinit simulation package with the multi-binit feature, but understandably this feature is strongly tied to Abinit's input-output formats and workflow, and we also may like to use certain features of other DFT packages which aren't yet available in Abinit, such as van der Waals density functionals. Therefore, we've been developing an alternative implementation of the second principles approach, which use YAML and HDF5 for input and output. And so in principle, one can generate training data using any DFT code and post-process this output into these open formats, and then use Chronic, which is the name I've given to this implementation, to train a second principles effective Hamiltonian. And so I've been using Chronic to train a model for chloronic acid, and in this case, the high symmetry phase of chloronic acid has the PVCM space group, and so the potential energy is defined relative to this state. And I've been using CP2K and the van der Waals DF2 exchange and correlation functional on a 2x2x2 supercell of chloronic acid for the training data. So in principle, the second principles approach allows one to fit terms at any order of the atomic displacements. However, in practice, it's more efficient to pre-calculate the harmonic terms, so the terms which are quadratic in atomic displacements, using either density functional perturbation theory or finite differences with DFT. as implemented in Funnapy, for example. And so that's what I've done in this case. And so the forward selection algorithm then fits only the anharmonic part of the potential energy surface. Harmonic force constants are defined for a supercell of particular shape and size. And so there's a question of how to extend a model trained in this way to a supercell of arbitrary dimension. And so the approach that we've taken is to assume that we can separate each force constant component into electrostatic and non-electrostatic parts, and then calculate the electrostatic part independently using the smooth particle mesh Ewaldson algorithm, which has also been implemented in Chronic. And then assume we can attribute the non-electrostatic part of the force constant to the most proximal image of the interaction captured by this force constant component. So the figure on the right is an attempt to illustrate that. So the green arrow shows the most proximal image of the interaction between a pair of protons in a 2x2x2 supercell of carbonic acid. And the blue arrows indicate other images of this interaction which are have a greater separation, and so are less significant. And so in this case, the non-electrostatic part of the interaction will be attributed to the image with the green, illustrated by the green arrow. So the pool of terms which capture all carbon, oxygen, and hydrogen atom displacements, consistent with a maximum order of terms of 4 and a spatial cutoff of 11 Bohr, which is the width of one of these kind of molecular rings in carbonic acid, gives a pool of terms on the order of which has a size on the order of 100,000, and so this makes training quite expensive and time-consuming. And so for the time being, I've been focusing on a fixed string model where the carbon and oxygen atoms are fixed and only the protons have freedom. And I've been trying to see if this kind of simplified model retains most of the important physics which occur during the polarization switching of carbonic acid. So this is an example of a model which I've trained. So after 50 fitted terms, I've reached a root mean squared error in the forces on the test split of my trained data set of 0.03 electron volts per angstrom, which is comparable to other effective Hamiltonians or interatomic force fields, which are kind of cited in the literature. So I've been using this effective Hamiltonian to carry out kinetic Monte Carlo simulations on a 2x8x2 supercell of carbonic acid in order to understand the polarization switching mechanism. I decided to extend the supercell in the crystallographic B direction because the plates of carbonic acid, which are used in experiments like the terahertz imaging example I showed before, they also extend, the plates are extended in this dimension as well as the polar axis direction. I discretized the potential energy surface by allowing each atomic displacement component to take one of 3 evenly spaced values between the domain states, illustrated in the 2 figures on the right. So what I found is that if I initialize the configuration to a homogeneous negative domain state. So all of the protons on the, say, the left side of the gap in the bottom figure on this slide, I find homogeneous switching within 7 picoseconds for an applied field of 4,000 kilovolts per centimeter, which is several orders of magnitude greater than the experimental coercive field, which can be explained by the fact that at the moment the effective defects aren't captured by this model, which usually acts as domain nucleation sites. And the absence of defects in the model also means that there's no domain nucleation and growth mechanism observable in this case. And so to kind of simulate the domain growth phase of the polarization switching, I pre-nucleated a domain at y equals 0 at the same temperature and the same applied field. And as a result of this, I find some domain growth behavior on both sides of the nucleus. So in the future, I'd like to extend this model to include carbon and oxygen atom distortions, and also include the effects of point defects to explore the domain nucleation phase to get a more complete picture of the polarization switching mechanism, and then to also explore the dependence of this mechanism on temperature. I'd like to thank the EPCC for supporting Archer and Archer 2, the EPSRC for funding my CDC on the theory and simulation of materials, which I'm a part of at Imperial, the MMM Hub for supporting Thomas and Young, and my supervisors, Laura Ratcliffe and Aaron Walsh, and our respective groups. And thank you all for your attention, and thanks for listening.
Thank you very much, Matthew. Does anybody have any questions? Okay, well, I'll get started with one. You're talking here about proton transfer, and of course, proton transfer involves a very light atom hopping between two potential wells. Do you think that the quantum mechanical nature of the nuclei might be important here?
Yeah, that is a possibility. And in other proton transfer ferroelectrics, for example, KDP, potassium dihydrogen phosphate, there has been evidence of tunneling of not single protons, but kind of clusters of atoms surrounding protons, which kind of influence the ferroelectric behavior. And so, yeah, that is something which I'd be interested in exploring after I've got the full model, including carbon and oxygen distortions,
of course, yeah,
trained.
Yeah, and you said this was a very expensive calculation, or sorry, a very expensive set of calculations. How expensive are we talking?
So it depends on the size of the pool of terms, but for this. So in the fixed string case, the size of the pool is much reduced, so I can train. So the model which I show the results of, I managed to train in about an hour, basically, on about 100 processes, because the forward selection, it parallelizes quite well, so that's quite good. Okay,
but we're talking days or weeks for the.
Yeah, I'd imagine, yeah.
Okay. Well,
yeah.
Very nice. Okay, thank you very much. Any other questions? No? Okay, I'm sure if you've got any, or if anyone else has got any, you'll be findable.
Sure.
So thank you very much. Let's pass on to Julia next. Hang on.
Yes.
There you go. Okay. So go ahead, the floor is yours.
Thank you. Can you see the presentation?
Yep.
Okay, perfect. Good, then thank you. And before we start, I want to thank the organizers for the opportunity to talk. And I'm going to talk about our latest research where we developed a machine learning model to describe excited states of functional organic molecules. So you might be familiar with machine learning, but now I want you to take a mental note that when we talk about, or when I talk about excited states, it means that we do not only fit one scalar value, but we fit many values simultaneously. So, and I want to dive into this topic by introducing fluorine. And fluorine is one of organic molecules that plays a fundamental role in the research field of optoelectronics. And this is due to its special optoelectronic properties. But it's not the only molecule that is important. There is also, for instance, phenanthrin. And while phenanthrin only differs by one carbon atom to fluorine, it exhibits different optoelectronic properties. And there are many more systems, such as members of the azine family. And depending on whom you ask, you might end up with about 10 to the power of 20 to 10 to the power of 60 functional organic molecules that could be of potential relevance in this research field. So if you want to design a new organic device and want to find a suitable molecule for your purpose, you might end up with searching for a needle in a haystack, because you need to screen many millions of molecules and characterize the optoelectronic properties. So this is, of course, problematic, but we could characterize the optoelectronic properties of such systems with photoelectron spectroscopy. So in photoelectron spectroscopy, we perturb a system via light. There is photoemission, where an electron is ejected. So we probe the energy levels of the occupied states. And you can see here that the energy level of the occupied state is equal to the ionization potential. On the other hand, we have inverse photoemission, where we can probe the unoccupied states, and instead of an electron that is ejected, now an electron is added. And the energy level of the unoccupied state is then equal to the negative of the electron affinity. And both the electron affinity and the ionization potential are fundamental properties to characterize organic molecules in optoelectronics. If we want to find out about these properties, there are two ways. So the first approach would be to go to the lab. So if you studied chemistry, you might know that doing experiments is quite expensive and also time consuming. But nevertheless, we can select a molecule, we can go to the lab and measure the photoelectron spectrum. But because it is time consuming, it is limited in the number of molecules that we can measure. And we also don't know if the molecule that we are interested in is synthesizable already. And that's exactly where theory can help a lot, because with theoretical calculations, we can compute the photoemission spectra of many molecules before we have to go to the lab. So we could screen a lot of different molecules, compute their spectra, and then select the most suitable molecules. But if we want spectra that are comparable to experiment, we need high accuracy. And unfortunately, methods that can deliver a good quality are too expensive to enable high throughput screening. So that was our idea, to replace the expensive quantum chemical calculations with a machine learning model that can learn the electronic structure of organic molecules and can be used to predict photoemission spectra. So there are different ways how we can use machine learning to complement photoelectron spectroscopy. And the most fundamental way would be to predict the primary output of a quantum chemical calculation. So this would mean that we fit the Hamiltonian in a local orbit representation. And if we do so, we can use this then to derive any properties we wish to know. So of course, this would be the most powerful approach. And the orbital energies we would get by diagonalization of this matrix. Unfortunately, this has not yet been achieved for many different molecules. And so there is another approach, which is fitting the secondary output directly, which would be fitting the orbital energies directly. So with this approach, we would still be able to define which energy level gives rise to which peak, and we could also compute the photoelectron spectra. And last but not least, there is also the approach to fit the tertiary output, which is most commonly used. In this case, we would fit the spectral functions, and we could discretize them into a certain amount of values and fit these values. So this is the most simplest approach because, and we all also guarantee that we have smooth functions. But in this case, we would lose the interpretability. So we would not be able to say, okay, this peak is due to these energy levels. And therefore, we went to fit the secondary outputs. So we wanted to find a machine or develop a machine learning model which we can use to fit many orbital energies simultaneously. So very briefly, in machine learning, we usually try to find a good relation between an input, which would be our molecular geometry, and the output, which would now be the orbital energies. And we could learn the relation by using a training set that contains both. And in our case, we have used a neural network. And by training, we then find the fitting parameters that connect the different nodes in the layers of the network, and we'll find the best relation between the input and the output. So there are two things that we had to decide in advance. And the first one was, how should we represent the molecules? So we have a lot of different molecules, and we need a rotationally and translationally invariant descriptor. And for this purpose, we have chosen SNET. And SNET is a message passing neural network, which is very powerful because it automatically learns the descriptor. So now it doesn't matter anymore if fluorine sits here or here, it always gives us the same orbital energies. The second ingredient that we needed was a data set that contained both the structures and the orbital energies. And for this purpose, we have chosen the OE62 spectroscopy data set, which contains a set of many diverse functional organic molecules. And I want to go into more details because this training set is very powerful. And it is so powerful because it contains molecular geometries of molecules that really exist. So they are not just made up by any theoreticians in many other data sets used in machine learning, but these structures are really extracted from organic crystals that were once synthesized. So we have 62,000 data points at PBE0 or level of theory. So please make a short note in your head. We have 62,000 data points. So you can see here the distribution of these molecules in this training set. You can see that we have a lot of small systems and also quite large ones. And these systems have many different elements. So the chemical diversity is very rich. But there's a problem which became apparent when we started to fit the orbital energies. And it is that orbital energies are non-smooth properties. And this is problematic for machine learning. So you can see here a reaction coordinate and the orbital energies along this coordinate. And in several regions along the reaction coordinate, you can see that the orbital energies approach each other and they want to cross. So they form an avoided crossing, but they do not cross. So they have cusps and they are non-smooth, which is problematic as machine learning models are smooth functions per definition. So the usual approach that we wanted to use, just use a normal machine learning model and fit the orbital energies, did not work. And therefore, we adapted our model such that the last layer of the network represents a latent Hamiltonian. So this would be somehow similar to the primary output, but it doesn't have any physical meaning. The only thing that is the same or equal to the real Hamiltonian is that after diagonalization, it gives us the orbital energies as eigenvalues of this matrix, and the matrix is also symmetric. So with this approach, we outsource the problem of non-smoothness by having something that is smooth. And it's much easier now to learn the orbital energies. And you can see here the matrix elements along the same reaction coordinate. And where we had an avoided crossing before, we now allow the curves to cross. So we then fitted the orbital energies with this approach, and we were quite happy because the fitting worked. And then we used this model to predict the photoemission spectrum of fluorine, and then we compared the experiment. And what you can see here is that the experimental spectrum does not really fit or is comparable to our predicted spectrum. So what we need, of course, was higher accuracy, because DFT is not the most suitable method for this purpose. And that's why I want to go back to the data set, because it also has some other features, and not only orbital energies at BB0 level of theory, because it also contains 5,000 data points at the GW level of theory. And this is really, really nice, because GW can correct DFT orbital energies that are wrong due to the neglect of the self-interaction energy. So this training set contains G0 W0 values, which is a single shot perturbation. It's the most simplest approach of GW. And the perturbation is the electron that is ejected at or added. So you can see here that we only have 5,000 data points, and there are the distribution in the training set. The molecules that are represented are also not that large, but the chemical diversity is also very rich. And the problem now that we faced was that we have the accuracy now that we need, but unfortunately, GW is way too expensive to compute many data points. So before we had 62,000, now we have 5,000 data points. So the question that we had to answer was, how can we learn from little data? And the approach that we used was delta machine learning for this purpose. So we know that there is a relation between the prediction accuracy and the number of data points that we have. So if we have the model from before that was trained on a 62,000 data points at a PBE0 level of theory, then we reach with the number of data points that we have our desired accuracy. So, but unfortunately, if we want to use the same model and train the 5,000 data points at the GW level, the accuracy decreases and we need more data, which is not feasible in this case. So what we did then was delta machine learning, as already mentioned, where we do not train a method directly, so the values of a method, but we train the difference between two methods. And the difference between two methods, like DFT and GW, is much smoother than training actual orbital energies. So you can see here that we also trained the second machine learning model, which is the difference between GW and DFT. And by combining these two models, we get the orbital energies at the GW level of theory. So that's exactly what we did. We trained one model on the PBE0 level of theory orbital energies, and then we trained a second model on the difference between the first model and the GW values. And with this, we were able to fit the quasi-particle energies. And I now want to show you the results of this approach. So here is the photo emission spectrum of fluorine from before, the one that we predicted with the first model, then the experimental spectrum. And now if we add the second neural network, so the delta machine learning model, you can see that the spectrum becomes comparable to experiment. And that's exactly what we wanted to achieve. And we also wanted to know whether we can distinguish between molecules that are similar. So we have chosen phenanthrene that I've introduced to you in the beginning. And again, you can see the spectrum that we predicted with the first model, then the experimental spectrum. And you can see that they do not match well. And then we add the delta machine learning model, and you can see that the spectrum becomes comparable again. Last but not least, we also wanted to see whether we can predict molecules of different conjugation length. So we have chosen the members of the acene family and predicted the electron affinity here and the ionization potential. In blue is the prediction, in orange the experimental values. And you can see that the trend of the gap between the electron affinity and the ionization potential decreases. That trend can be reproduced. However, you can also see that the values are slightly underestimated, but this is not an artifact of the machine learning model, but it's an artifact of GW. So we have learned this. Yes, so with this, I already want to come to the conclusion. I hope that I could show you that we developed a machine learning model with which we can predict orbital energies and quasi-particle energies of several different organic molecules. And it can be used to complement photo emission spectroscopy. And what we want to do is in the future is to do high throughput screening to find new systems with special optoelectronic properties. So we want to compute millions of molecules and predict their properties. And yes, last but not least, I want to thank my current research group at the University of Warwick, many funding agencies, Professor Reinhard Maurer, and some collaborators from Berlin. And I want to thank you for your attention.
Fantastic. Thank you very much. A nice example of delta learning there. That's lovely. We have a question. So what is the main difficulty in fitting the Hamiltonian directly in local orbitals?
So on one side, it is extremely large. If I understand correctly now, if we only have one system, this is usually very large, because we also have many, especially for DFT, if we have the unoccupied orbital energies, so the unoccupied cone-sham levels, these do not have any meaning, and they are also not very accurate or meaningful somehow, so it's very difficult to fit. And there is the Schnob machine learning model that was developed by Reinhard Maurer, and that's exactly what they saw. So they could fit the occupied states, but not the unoccupied states. And if we now go to different molecules, then the main problem is that the Hamiltonian has a different size for every system. So it is not transferable, because except for the HOMO and the LUMO. If we have H2, for instance, then we only have 2 electrons. But if we have much larger systems, we have many electrons. So we have much more orbital energies, and the Hamiltonian would become much larger. And it also depends on the basis set. So that's the main problem.
Okay, thank you. That is answered. So you want to scan through millions of molecules. How much time will you save by using the machine learning approach?
So for large systems, if we do a GW calculation on about, so I'm currently doing some calculations for molecules with 100 atoms, and it takes on high memory nodes with 100 CPUs, about 2 days. And machine learning takes not even a second. So we will save a lot.
That's quite impressive.
Yeah, GW has the main problem that it consumes a lot of memory.
Sure, that makes sense. That makes sense. Okay, very nice. Thank you. Any further questions? No? In that case, thank you again. And I will see if I can figure out how to unpin you from the screen. Okay. So,
all right.
Go ahead. The floor is yours.
Yeah, I hope you can hear me fine and you can see my screen. Looks like it, I think. All right. Yeah, before I start, let me also thank the organizers for giving me the opportunity to talk at this very nice conference. My name is Christoph Schran, and I'm from the group of Angelos Michailidis from Cambridge. And today I'm going to present you some results that have been published very recently in PNAS on machine learning potentials for complex aqueous systems and how to obtain those in a simple manner. But before I actually go into the methodology, I would like to motivate why or what I mean with complex aqueous systems, water in complex environments. And for that, I show you here a system that we have in mind that we would like to understand better. And that is, for example, water flowing through a carbon nanotube. And this is actually of high relevance for certain applications, such as nanofiltration or osmotic energy conversion, where you would harvest like energy of the water that is flowing through such a system. And it's also relevant in order to provide clean water supplies based on desalination applications. However, before we actually can realize like rational design of such applications, we actually have to solve some open questions. For example, how water actually flows through such systems and how like charge defects like ions are influenced under these confinement conditions. And then there's also like the material dependence. If you switch actually the interface material, that will have an impact on the water and how water behaves in such a system. So the methods we usually apply to study such systems are molecular dynamics simulations. And the main principles are that you propagate the Newton's equation of motion to propagate your system in time, and then you can afterwards analyze your trajectory in order to obtain dynamical or statistical properties of interest. However, in these simulations, a very central property, as all of you will know, is the potential energy surface of the system. And to highlight why this is such an important property, I like to show this small figure here, where you see the dependence of the contact angle of water on the binding energy to a surface. And you see that like really small changes in the binding energy on a few milli-eV actually have a large impact on this droplet contact angle. So it's crucial if we are looking for like water in complex environments to get a highly accurate description of the potential energy surface. And like off-the-shelf methods are either ab initio methods or force field methods, and both come with certain advantages and disadvantages. On the one hand, ab initio methods, where I mainly mean DFT-based methods, usually have the required accuracy that we would like to have, but they are expensive and slow. Whereas the force field methods can go to the system sizes we are interested in, but are usually lacking on the accuracy. And the whole purpose of the talk that I'm presenting today is to use machine learning in order to get the best of the two worlds. We want the high accuracy, but the fast evaluation. All right, we've already seen quite a lot of talks on machine learning in this conference, but still I would like to give you my point of view of machine learning potentials, like in a nutshell, basically. And for that, actually most of the machine learning potentials on the market kind of like use the same principles that I show you here in the top figure. The main purpose of what we are trying to achieve is that we would like to represent the structure-energy relationship and also get forces for dynamical for molecular dynamics. And this is usually realized in this setup, that we first transform our structure into, like, based on descriptors, into a meaningful representation, and then we use a machine learning regression model to output our energies and forces. And so both, for example, the neural network potentials pioneered by Jörg Behler or the kernel-based GAP models by Gabachani are based on such a principle. And then another important ingredient is actually a locality of most of these models. So you concentrate only on the chemical environment of each atom in a certain cutoff. And then the whole purpose of the machine learning is that you build a representative training set, shown here for an arbitrary feature space. And afterwards, after you have built that training set and the model, you're able to interpolate between all the blue dots for a new point in question that you encounter in your simulation. However, there are certain challenges, in particular when it comes to complex systems. And that is, first of all, to actually construct a robust and accurate structure-energy relationship. Then the next one is to build up the representative training set for the application you have in mind. And finally, you also need to validate the resulting model in order to really trust what you have built. And in this work that I'm presenting today, we think we have come up with an end-to-end framework like that makes progress on all of these aspects in order to really tackle complex systems in a simple manner. And the main conceptual ideas behind what we are doing is that we concentrate on a specific thermodynamic condition. So this, first of all, makes it like an easier job to do compared to like obtaining a global machine learning model that could, for example, represent all the phases of carbon. This can also be done, but it's a much harder job. And then on top of that, we try to remove as much of the user input as possible and automate most of the development steps. And finally, we have also come up with an automated validation method, which we think is able to really streamline like this whole process, so that you kind of have an end-to-end framework from a question you have to a machine learning model that answers this question. And another aspect is that we build only on open source software and also make our code freely available so that the community can use it. Now let's come first of all to this, like what we actually use in terms of machine learning. So this builds on the high-dimensional neural network potential approach, as I said, like pioneered by Jörg Behler. And I will not go into any details here. As I said, I've already shown the rough principles of how the structure-energy relationship is achieved. Just a brief summary again, we first transform the structure into meaningful input based on, in this case, atom-centered symmetry functions, and then we do like regression of these inputs to obtain the potential energy surface. And training of such models can, for example, be done with the N2P2 software, which has been developed by the Delago group. And simulations are either possible in CP2K with an implementation that I have provided, or with LEMS, which also has an open source driver. However, we don't use this this normal high-dimensional neural network flavor, but instead go a step further and instead apply so-called committee models. And this is actually a very simple but powerful extension to the original method. And let me briefly describe the principle behind that. So imagine you have a potential energy surface shown here in black at the top of this figure, and you have already selected some training data from this potential energy surface. What you can then do is you can perform multiple fits of your machine learning model with, for example, variable initial condition, and then end up with different models that have more or less or good or worse prediction, actually. And usually, previously, you would have taken the best performing model and you would throw away all the others. But instead, what you can also do is you keep all these models that you have obtained and use the average of all of them as your new predictor. And that actually increases your accuracy quite a bit. And on top of that, you have access to the variance between all the different models. And that is a very powerful estimate of your uncertainty. And you can make use of that to actually improve your model by, for example, selecting regions with high uncertainty and adding new training data in these regions. So this is an active learning strategy called query by committee. And with that procedure, you can actually iteratively improve your model to get a better prediction and like smaller uncertainty. And these benefits of committees have been realized by different people, for example, the Marketor group or also the Cheriotti group. And we actually think that this is a very powerful extension without too much overhead to enable like this end-to-end framework that we have in mind. So how do we make use of this machine learning method? The whole procedure looks like that. As an input, we run a relatively small and short ab initio trajectory at the condition that we are actually interested in. And this ab initio trajectory is then fed into our automated active learning framework, which iteratively selects the most representative structures of the ab initio trajectory and builds up the training set and the resulting model. And then the resulting model can afterwards be applied to larger system sizes and longer simulation times to actually answer the questions you want to answer for the particular system you selected. And this is a really rapid workflow. So from the ab initio trajectory, once you have it, you can obtain the model in a very short amount of time, essentially in 1 or 2 days. So which makes this a rather helpful tool. And for what kind of systems have we applied this methodology? This is shown here in this slide. We have concentrated on aqueous phase systems, but like ions in solution, water in carbon nanotubes, and also HBN nanotubes, up to water in under confinement. For example, here water between MOS2 sheets and water on titanium dioxide surfaces. And for all of these systems, which have really like a large variety of properties and species in them, we have built the models with the same workflow and the same parameters by roughly selecting 300 structures from the relatively short ab initio simulation. With short, I mean something like 30 picoseconds. But that brings me to the next kind of question, and that's the validation of all these models. Like, sure, we can build those models, but we have to trust them in the end. And for that, we have come up with an automated testing procedure to compare the accuracy of the different models over the different systems. And this concentrates on three crucial properties of that you can evaluate for any system you like. And so the first one is a structural property based on the radial distribution function of the system. For example, shown here on the left for the fluoride water system. Then the next property we have selected is the vibrational density of states, which is a dynamical property and gives us an idea of the different intra and intermolecular modes of the system of interest. And then finally, we concentrate on a machine learning property, so the force correlation between our model and our reference method. And we use all these properties and evaluate them for all the different systems we have, compare them to our ab initio prediction, and then reduce them into a final score for all these three categories. And that actually allows us to make a very simple and direct comparison between all the different models and systems we have developed. And so this performance summary is shown here in this slide. And first of all, what you will notice is that all of them, all of the different models for the different systems actually achieve very high accuracy compared to the ab initio method, where the radial distribution function usually scores the best, whereas the forces have the lowest score, ranging from like 88% or 87% to roughly 93%. What is also nice is that all of them have, roughly speaking, the same accuracy for these very different systems. This summary might look arbitrary, but we are convinced that this is actually a meaningful measure because we have also evaluated other properties like hydrogen bonding, the density profiles, water orientations, and overall see a good agreement with our reference, so that we think this automated testing is a nice summary of the accuracy of your developed model. And now let's finally come to an actual application, what we can do with such a model. And for that, I concentrate on this system or this model developed for water on the rutile titanium dioxide surface. So this system is actually relevant for photocatalysis or coatings and pigments. And a snapshot of the system is shown here in the left top panel. The original ab initio method, or ab initio MD, has been 30 picoseconds with roughly 400 atoms. And with the final model that we have obtained, we can easily run nanosecond simulations for an extended system size. And here I show like different properties evaluated for the system. First of all, the density profile as a function of the height of the water slab on the surface. And you will notice there that we actually end up with a highly structured water arrangement on this titanium dioxide surface, where our machine learning prediction agrees well with the ab initio MD, but the ab initio MD is kind of like a very crude profile. So to converge that, we really need the long simulation time. And this long simulation time also enables us to evaluate other properties that we simply can't access with such a short ab initio MD. For example, the distance resolved diffusion constant of water on this titanium dioxide system. There you see that both the lateral and perpendicular diffusion actually is very much perturbed up to roughly 1 nanometer into the liquid. And we end up with an almost immobile first contact layer, which is relevant, for example, when it comes to photocatalysis and applications where water needs to move on the surface. And another aspect that is kind of nice is that we still have access to this intrinsic error estimate of our model and can also resolve that both as a function of time or as a function of the water slab. And we overall see like really good accuracy for this error estimate, which makes us like really trust these results, although they have been significantly extended over the original ab initio MD. All right, and that already brings me to the summary of today's talk. I think I've shown you how the challenge of like getting to large system sizes and long simulation times at high accuracy can be achieved with machine learning for these complex aqueous systems. And we think that we have come up with kind of a rapid and simple process to develop these models. And overall, we see convincing accuracy for all systems. And all that is open source development, so you can actually go to that paper, check out the code, and use it for your own work if you want. And an outlook to what I've presented is that this enables us to really go to long sampling time and large system sizes in order to converge properties, for example, like friction on the surface or viscosity at interfaces, and study these processes in more detail for complex aqueous systems. And with that, I like to acknowledge the other co-authors of the paper. First of all, Fabian and Patrick, the two PhD students in the group, and then Eric Müller from Imperial, Andrei Mazalek from the Charles University, and finally Angelos Michailidis from Cambridge. And with that, I conclude and also thank the funding agencies, both for the resources and my own position. And now I thank also you, of course, for your attention and look forward to any questions you might have.
Great. Thank you very much, Christoph. We do have a few questions, and we have some time for it. So here we go. From Julia, thank you for this great presentation of your recent work. I was wondering whether you train separate models on your selected system or one model on all systems. Is it better to train on all systems or on one?
Yeah, so all these various systems have been described with an individual model, and that actually makes the job again easier because we are trying really to get a model for a particular system and a particular condition, and that actually is a much easier job than being able to describe all these variable systems with similar accuracy over all these different chemical environments. And I think this is actually a key point in what we are trying to do here. We are not after the perfect model for water under confinement. We would rather have a framework that gives us a model in a short amount of time so that we can look at the questions we are interested in.
Thank you. So next is, how do you make sure the ab initio MD trajectory is well equilibrated and doesn't have any serious finite size effects before you compare the structural properties like the RDF to the machine learning predicted one, which I assume comes from larger systems and longer timescales? The timescales being a separate question.
Yeah, so this is actually like an important factor. I might have been a bit too fast there, but when I say small and short ab initio MD, this might still be considered large for certain people, and it's still like computational. This is still the biggest computational bottleneck actually. So you have to make sure that your actual ab initio trajectory is properly done, and it's not just like one water molecule on these surfaces on a small slab. So this is still an important ingredient, and we would you need some experience with ab initio MD in order to evaluate if the selected system sizes and timescales are meaningful enough. However, what we are also trying right now is to replace the ab initio MD actually with force field based structure generation in the first round of our training in order to prevent such questions, so that you're not having the bottleneck of expensive ab initio MD. And the idea there would be that you generate the structures with force field MD and then only call for certain structures you selected your expensive quantum engine to get the forces and energies.
Okay, thank you. We've got time for maybe one or two more questions, which is good because we have one or two more questions. Before we go to those, just let me remind you, it wasn't in the program that was emailed out, but at 4:05, there's a plenary closing session. So please all go to that for some closing remarks. So let's just have a couple more questions before we get to that. So Andrew says, nice talk. I note for the titanium dioxide H2O system that you don't have surface hydrogenation or protonation, which one might expect in a solvated environment. Are the models capable of handling changes in chemistry at the surface of this sort of realistic nature?
Yeah, that's actually a good question. And like the titanium dioxide water setup is actually a highly controversial one. And so what I can say on that particular electronic structure setup that we have selected is that we do not observe protonation and dissociation of the water. And we also don't observe that for the long simulation times we have looked at. However, this will depend very much on the functional you choose. Still, we think if we are not looking at this particular question, if we are rather after, for example, the structuring of water and the mobility of water, then we can still select a decent functional as we have done and answer those particular questions. But we haven't looked specifically into the protonation because the DFT method will not have dissociated water for the particular